Okay, in this video we're going to do an introduction on matrices, and this section focuses on how we can use them to solve systems of equations. So for a matrix, the dimensions are defined by two numbers, m and n, and they have to be integers. So you have things like 1 by 2 matrices, 3 by 3 matrices, blank by blank. Those numbers have to be positive integers. Alright, the order is the number of rows by the number of columns. The rows go horizontally and the columns go vertically. So always think row by column, row by column. And if m and n are equal, the rows and columns are equal, then we call that a square matrix. A matrix with only one row is called a row matrix, something like this, 1, 2, 3, that only has one row. A column matrix only has one column, so that could be something like this, 1, 1, 1, 1. Alright, so the order is just another way to say the dimensions. So pause the video and find the order of these four matrices right on the bottom of the page here. Okay, so number one is a 2 by 4. So it has 2 rows by 4 columns. This would be a square matrix, that's a 2 by 2. This would be a 4 by 2. And then this number 4 here is just a 1 by 1 matrix. Alright, so to augment something means to like change it, make it bigger. So an augmented matrix refers to taking a system of equations, like this one over here on the left, and representing it as a matrix. So what you do is write the system in standard form, where it's x terms, y terms, z terms, and then equals your constant terms. Alright, and then if you write it all them in standard form, you see that this first column corresponds with this top equation, the second column corresponds with the second equation, and the third column, row, corresponds with the third equation. Sorry, they're all rows. I don't know. So this is row 1, row 2, row 3. They correspond with these three equations. All right, the first column corresponds with the x coordinates, the second one the y coordinates, and then the third one the z coordinates. Alright, so that's what an augmented matrix is, just writing the matrix as a system. This first part here, also rewritten here, is just called the coefficient matrix. Before we get into using these, why don't you pause the video and try to rewrite number 5 as an augmented matrix. Okay, so on the right, in purple, that's the augmented matrix. That's the answer you should have. If you change the rows, that's okay. You can interchange rows and it still means the same thing. But the one thing that you may be messed up on is make sure that you put this, you put it in standard form. So you have to rewrite the, you have to rewrite these equations in standard form. X, Y, Z. Then you can write it as an augmented matrix. Alright, now let's look at a couple more things and then we'll solve the system. Alright, so some vocab. So an identity matrix is a square matrix, so it's got to be a 2 by 2 or a 3 by 3, where each entry is 0. And the main diagonal are all 1s. So that's what a 3 by 3 identity matrix looks like. This would be the main diagonal from one corner to the other, and then everything else is just zeros. So why don't you pause the video real quick and write a 2 by 2 identity matrix. Alright, so that's what it should look like. That would be a 2 by 2 identity matrix. A 4 by 4 would just be like this 3 by 3, except add another row and column, and you solve that diagonal of once. For a reduced row echelon form, so that's when you take like a augmented matrix that usually represents a system of equations and do Gaussian elimination like we did in Chapter 9 when we did elimination to solve systems of equations. And reduced row echelon form is when you get this coefficient matrix as the identity matrix. And what the beauty of that is you could just solve the system once you get it in this form, right? If this is the x, the y, and the z terms, if you solve the system and put it in reduced row echelon form, you would know x is 5, y is 4, and z is 6. Alright, so that's the goal when we solve the system. We want to add equations or rows of matrices to each other to get our matrix down to reduced row echelon form.